Okay, so I'm just going to tell a little story about atmospheric chemistry today, and hopefully explain some of the science in the field and the different physical processes that we're interested in this area of research. And then we'll do a little experiment with the Erlenmeyer flasks that I have sitting over there, and those two clementines. We'll see how that's related to our atmosphere momentarily. But just the most basic background. In atmospheric chemistry, our sort of reaction vesicle that we're interested in is the atmosphere. So we have to be aware of the constituents that are in that vessel. And most of dry air is just, of course, nitrogen. And then we also have about 21% oxygen and then 1% argon, and then a bunch of other trace gases. And it's really the oxygen and the other trace gases that we're going to be interested in. And that's what's going to drive a lot of the chemistry that we're concerned with. And I just want to go over one specific example today, which will sort of lead into a lot of areas that actually modern atmospheric chemists are concerned with. But this particular example goes back to the mid-20th century, so during actually World War II in Los Angeles on this date, July 26, 1943. One morning, this sort of thick fog happened to appear. And it wasn't just like a cloud sitting at the ground level, no, it actually was quite irritating to breathe in. So you can see on this photo here is actually from that specific day. The photo on the right is actually from much later. This gentleman in 1950s attire with, wiping his eyes because breathing in this, what turned out to be photochemical smog, it really makes your eyes water, and then also, really irritates the throat. So what's going on here? Well, at the time, they, of course, had no idea. The mayor of Los Angeles promised that we'd figure this out in 6 months, but it actually took close to a decade to figure out what the source of this photochemical smog was. So another broken promise from a politician. But what is sort of a color photo of photochemical smog, the more familiar picture? You can see this sort of orange tinge here, and so not only does it have this orange color, but it also has this greatly reduced visibility. So what's going on here, and why did it take so long to figure out? Well, the gentleman who put all the pieces together was this Dutch organic chemist who happened to be working in agriculture in Southern California at the time, Harry Hagen-Smit. And he figured out that the source of the smog was originating from tailpipes of cars. Now that may seem obvious to us now, but the issue is the main component of the smog was ozone, and ozone is not directly emitted from the tailpipe of a car. So there had to be several steps in between the generation of the ozone that leads to a lot of the chemistry and the photochemical smog and what was coming out of the tailpipe. Here we see a nice picture of Hagen-Smit sitting in his laboratory smoking a cigarette next to what we can only assume are flammable chemicals. He did die of lung cancer, so don't smoke. Okay, so what is actual smog, and what did Hagen-Smit call it? So it's often just called an ozone layer in the wrong place. So we have the ozone layer, of course, up in the stratosphere, tens of kilometers above us. That's good because it shields a lot of UV radiation. But then when we have a smog event, or a photochemical smog event specifically, we have a lot of ozone at the ground level. And this is bad to breathe in. That's what leads to a lot of the irritation that gentleman was experiencing. And basically what Hagen-Smit pointed out was you need 4 ingredients to have this smog event. You need volatile organic compounds, I'll get to that. Oxygen, no problem in our atmosphere. Nitric oxide, and then also sunlight. So in sunny Los Angeles, the 2 and 4, no problem. Where do the other components come from? Well, we already said it comes out of the tailpipe. So if we just look at the internal combustion engine, here's just an animation showing the 4-stroke engine. We have this chemistry that you may be familiar with if you've taken like your basic chemistry course. It's just the combustion here. So we have gasoline plus oxygen to carbon dioxide and water, right? This is the complete combustion reaction. So gasoline is a bunch of different molecules, but we're just showing octane here, right? So you get octane plus O2 and then the spark, and then it releases a bunch of energy and you form CO2 and H2O. So that's fine, but we also get a bunch of side reactions because there is so much energy. Things like that would normally never happen in the atmosphere, like N2 and O2 forming NO, nitric oxide. So we're now generating some NO, and you also get other reactions here where you get NO2. So these are collectively called NOx. So out of the tailpipe, you get mainly CO2 and H2O. That's okay. But then you also get NOx, and then you also get things like from incomplete combustion, like CO, and then also just like gas, gas that didn't completely burn, so just other hydrocarbons coming out. So those will be what we call volatile organic compounds. These are molecules that want to just be in the vapor phase. They don't want to condense. So when you have all these things and then the right conditions, like was in that paper, you can start to get some interesting chemistry taking place. specifically with NO2, and this is actually what ultimately leads to the formation of the ozone that Hagen-Smith, well, that was already known to occur, but this is the actual pathway. So you have this NO2 that's formed. After you get all the NOx coming out, you just start to generate a bunch of NO2 in the atmosphere. And then if you have visible light, which you do, of course, in the morning rush hour, that can actually break apart this NO2 molecule. So NO2 is interesting because it absorbs in the visible part of the spectrum where a lot of these other molecules do not. So blue light will just break it apart, and you get atomic oxygen from that, and that reacts with O2 that gives us our ozone molecules. So our ozone layer that does all the chemistry or most of the chemistry, at least in the photochemical smog event. And you can actually see a flask here of NO2, and it has sort of this brown yellowish color because it's absorbing in the blue, so it looks yellow. All right, so our experiment today will be what happens with some of that ozone in those VOCs, those volatile organic compounds, which I mentioned at the beginning. And we're going to look at the oxidation of one of these volatile organic compounds, in this case, one that's easy to generate in this room, which is limonene, which when you peel an orange, that smell you have from the orange, that's this molecule here, limonene, actually comes in two mirror images. One smells like oranges and one smells like lemon, so that's an interesting piece of chemistry trivia. So it's a terpene, and it'll be oxidized by ozone. So over there in the flask over the last few minutes, let's just see how long I have, 10 minutes, which is enough. I had this little UV lamp going, so this. So I'm not generating it the way it would be done in the atmosphere because I don't want to get a bunch of NO and NO2. So I've just been using this UV lamp, which can break apart oxygen and generate atomic oxygen and then ozone. So I have a bunch of ozone now in this flask. And what I'm just going to do is peel one of these clementines and drop the peels in and see if we can, so all that orangey smell, that limonene, if it's oxidized by the ozone. And maybe we'll get some results out of that. So let's just start dropping some peels in. This is the most exciting part of the talk. We've got too much peel and orange. And then you can so just do that. What we can now see, it's a bit tough to see from there because it's not that thick of a cloud. But if I had, say, a flask with nothing in it and I shine this green laser through, nothing really happens. But with this one, now we can see there's a green beam because there's now some small particles in there, right, scattering a lot of light. So what's happening, what's going on in this situation, we can try to understand. And actually, I don't know if I really want to pass this around, but if you hold it up to a light and look at it through this, it does actually look quite clear. So actually, maybe I can. I don't know if anyone's interested in that, just don't draw it, because it'll stick. So what's actually taking place here? Well, so I had that UV lamp, I generated ozone, I explained that already. That's actually how ozone's generated in the atmosphere, or in the stratosphere, pardon me, not during a photochemical smog event. And then with this ozone in the terpene, limonene in this case, there's sort of a complex series of reactions, but basically you're just oxidizing this molecule, and it gets more polar, and then it doesn't want to be in the vapor phase as much, so it condenses into tiny droplets. So there's all this chemistry taking place, and then the product is not volatile, so it condenses into tiny particles, and those scatter light very, very efficiently, so it looks sort of cloudy when that happens. And then you get a cloudy flask color. So it's these tiny, tiny particles that are actually only about, in this case, they'll be a few hundred nanometers, so very, very small. And if I did this experiment with an actual ozone generator as opposed to my toy UV lamp, you'd get a much more cloudy, there's a more dramatic example of the experiment there. And so is smog still a problem? So there's way more cars in Los Angeles nowadays. Did everyone switch to electric cars? No, that's not what actually happened. Sort of the process that improved it got rid of a lot of the smog issues in California at least was more efficient engines. So the ICE engine is now way more efficient than it was in the 40s. And also the introduction of catalytic converters, which are, come before the muffler. And what these do is they basically take these products from incomplete combustion and change the carbon ones into CO2 and H2O, and then the NOx ones into N2. So that gets rid of a lot of that. The introduction of the catalytic converter solves a lot of those issues. But smog in different forms, not necessarily the photochemical one, is still an issue in different places. So we have here this from Beijing where they burn a lot of coal, so that's a result of that. And there's different types of smog as well. Again, burning coal is not great because you generate a bunch of sulfur compounds that can lead to the formation of sulfuric acid, like in that. And yeah, a lot of coal burning. And then there's other types of tiny particles that we have to be aware of, like from last summer, right? The wildfires generate a lot of brown carbon particles and black carbon particles, and of course, reduce visibility, but more dramatically when you're outside. You know, if anyone went out that day, it smelled like you're next to a campfire, right? It was really depressing. So that's just a little tour of some of the issues and problems that we're interested in the field of atmospheric chemistry. And so thanks for your time, and hopefully you enjoyed the orange demonstration.